Hey everyone, in this AP Chem series video, we're going to take a look at the periodic trend in electron affinity. First, remember that electron affinity is the energy released or absorbed when an atom acquires an electron. Like this chlorine atom, for example, if we gave it an electron, it would turn into chlorine -1 and energy would be released in the process. We represent that energy is being released by writing it on the products side in the equation. If you looked it up, you'd find that chlorine's electron affinity is reported as -349 kilojoules, which simply means that when this chlorine atom gained that electron, it released 349 kilojoules of energy. If you did the same thing with a bromine atom, you'd find that it only releases 324 kilojoules of energy. And a larger electron affinity magnitude tells me that an atom has a greater affinity for electrons or is more likely to gain them. Here, that means that chlorine is the atom that's more likely to gain electrons. In this video, we're going to take a look at how this property of electron affinity changes on the periodic table. The trend in electron affinity is much less predictable than some of the other trends we've studied so far, but a general pattern does exist. Here's a periodic table where we can label what's going on. Electron affinity tends to increase as you move from left to right and from bottom to top on the periodic table. That means the top right-hand corner are the atoms with the highest electron affinity values, and the bottom left have the lowest electron affinity values. We can see this pattern played out looking at one specific column from the periodic table known as the halogens. Iodine at the bottom has a lower electron affinity, and that value increases as you go up, although you'll notice the pattern breaks a little bit with a slight decrease from chlorine to fluorine. We can explain this trend in pretty much the same way we've explained the other trends. Let's analyze the nuclear charge of each of the atoms in the column along with the electron configuration. Let's start by calculating the approximate effective nuclear charge of each of these atoms. For chlorine, it has a +17 nucleus, but that is shielded by 10 inner core electrons, leaving me with an effective nuclear charge of about +7. If you did the same thing for bromine, you'd find that it also has a +7, and iodine also has an effective nuclear charge of +7. So just like within any column on the periodic table, the effective nuclear charge remains pretty much constant. This means that the differences we see in electron affinity between the atoms has to do with the outermost valence shells that the electrons get added into. In chlorine, for example, if I were to give it an electron, that electron is going to enter the outermost valence shell, in this case the 3p's. The 3p's are closer to the nucleus, so when the electron is added there, a stronger attraction forms between that electron and the nucleus. Compare that to adding an electron to an iodine atom where it has to go into the 5p orbitals. Those 5p orbitals are much farther from the nucleus, so a much weaker attraction forms. The formation of a stronger attraction like we'll have with the chlorine atom results in more energy being released, and therefore chlorine having a greater electron affinity value. We can summarize this by saying that electron affinity increases towards the top of the group due to increased attraction between the acquired electrons and the nucleus. When the acquired electron is added to a lower energy level, it is closer to that nucleus and therefore more attracted to it. Since a stronger attraction is formed, more energy is released and a greater electron affinity is observed. These are some of the key ideas related to electron affinity. Make sure you pause and take a moment to write them all down. Just like always in chemistry, you may notice or hear that there are exceptions to this general trend, and for electron affinity, there's lots of them. We can see that here where there's an increase from iodine to bromine to chlorine, but then a slight decrease down to fluorine's -328. The good news is that as of 2020, the AP Chem exam shouldn't ask you why these differences exist, so they won't be covered in this video. And that wraps it up for this video on electron affinity. Thanks for watching, and here's a brief summary.